Chapter external flow force convection. So now we gonna learn about the flow across tube banks. So when you finish studying this chapter, you should be able to 1. Evaluate the convection coefficients in external flow for tube bank, okay, for both laminar and turbulent flow. Okay, cross flow over tube banks is commonly encountered in practice in heat transfer equipment such as heat exchanger. So for example, if you can see in this figure, we have cross flow, we have tube here, and then cross flow means that this flow is crossing to the tubes, okay, external tubes, okay. In such equipment, one fluid moves through the tubes while the other moves over the tubes in perpendicular direction. Okay, the tubes, we have tubes and then we have perpendicular directions of fluid. Flow through the tubes can be analyzed by considering flow through a single tube and multiplying the results by the number of tubes. So in the practice of analyzing heat transfer for the heat exchanger, we use a lot of tubes. Therefore, in order for us to determine what is the rate of heat transfer for the heat shell and tube heat exchanger, for example, shell and tubes heat exchanger contains a lot of tubes. Therefore, in order for us to analyze, we have to calculate one tubes and then we multiply with how many tubes inside the heat exchanger. For flow over the tubes affect the flow patterns and turbulent level downstream, and thus heat transfer to or from them are altered. So there are two typical arrangements for tubes in the heat exchanger. One is inline, second is staggered. You can see the figure below. So we have inline arrangement where the fluid is inline to each other. So right here. And then staggered, the design, the arrangement of the tubes will be like this. Okay. So the outer diameter D is the characteristic length. Okay, the tubes have a thickness, and then we will use the characteristic length of the tubes is diameter outside, so external diameter, or outer tube or outer cylinder. Okay, so the arrangement of the tubes are characterized by the first one is transverse pitch. So ST here, from this point center of the tubes to the other center of the tubes, it will be transverse pitch ST. So longitudinal pitch SL. So SL is longitudinal, and here in the staggered arrangement, so SL is from this center of the tube to the center of the tube here. So we have SL. So the length of this is SL. Next is diagonal pitch SD. So SD is the length of from this center to this center. So we have SD. SL is from here, tube to the tubes. So we have SL, longitudinal pitch. And then SD is from center of this tube to the center of the other tubes. Okay. Normally, diagonal pitch is in staggered arrangement because we have diagonal pitch. So diagonal arrangement here in staggered. Okay, as the fluid enters the tube, the flow area decreases, okay, from A1 to AT. Take a look at this figure for inline arrangement. We have here, so we have AT area here. From here to here is A1. So here to here is area 1, and then we have AT. So the flow here, so as we can see here, so as the fluid enters the tube bank, the flow area decreases. So area of A1 and AT, it will decrease. So A1 much more bigger compared to AT. So between the tubes, and thus flow velocity increases. As it passes from A1 to AT, it will increase the velocity because of the area is decreasing. When the area is decreasing, then the velocity will increase. Okay. In the tube banks, the flow characteristics are dominated by the maximum velocity, so Vmax. So in the Reynolds number equation, you have to change from previously, you know that Reynolds number will be using rho velocity times width diameter divided by mu. Now we have to change. The velocity will not be the velocity of the flow, okay, flow of the fluid. We have to change the velocity here into V max. So the equation becomes rho V max d over mu. D will be diameter outside. So if we change into another form where we want to use a kinematic viscosity in the equation, therefore the equation becomes V max d outer over V. So for inline arrangement, the maximum velocity occurs at the minimum flow area between the tubes. So Vmax equal to St over St minus d times with V. Let's take a look how the V maximum becomes like that. So the equation becomes like that. So from this figure, so we know that A1 is much more greater than AT. So what we are going to do here is we want to find what is the V maximum. Okay. So we will use the equations. We know that here we have a conservation of mass. So mass 1 equal to mass at T. Am I right? So at this point, we know that AT, the area for T is much more smaller than area at 1. So AT has V maximum. When the area is decreasing, the velocity will be increased. At this point, when we compare between A1 and AT, V maximum occurs at AT. Therefore, in this equation, we will write density 1, velocity 1 times width, area 1 equal to rho at T, V, we will not put Vt because we know that Vt is V maximum, therefore here will be V maximum. And then area T. From here, we rearrange this equation. V maximum is equal to rho 1 V1 A1 over rho T A T. Okay. So let's take a look at area. So if this is the cross section of the tube. If we can see from here, front for the front if we can see here, so the tubes will become like this. Okay, we have these kinds of arrangement. So the area becomes, so I change the pen color first to the blue. So we want to find what is the area here. So this point is here. I put it 1, for example. So point here is 2. This is point 1 and this is point 2. So we want to find what is the area of this side. So to find the area, we have to multiply length with this length. So this length is ST. Therefore, for the area A1 equal to ST times with L. Okay, that is for the first area, area 1. So we want to find what is the area 2. So the area 2, area T is, this is AT. Previously, we already calculate this area, area 1. We want to find what is the AT. So to find AT, we have length of the tube and then times with ST. Oh, sorry. This one, we know that we want to find from this point to this point. We are only have ST value. For example, here is diameter. So this is radius of the tubes. And then this is also radius of the tube. If we can see here, we want to find what is the AT, we have to minus, so the area, the length for ST2, not length for ST, length for AT, we want to find length for AT, we have to, I wrote down here, so ST, you have to minus with diameter over 2, and then this is first diameter minus 2. When you divide by 2, you will have radius for here, and then we want to find this diameter also, so minus d over 2. So as you can see here, I bring it down, so it will become ST minus 2d over 2. So we can cancel out 2, therefore it will become ST minus d. So we know that this length, change it to the other color, so green. So we know that the length of at this point is equivalent to this. Okay, therefore area for ST becomes ST minus D times with L. Okay, for the AT, area T. So we know both area equation, then we substitute into this equation. So V max equal to rho 1 over rho T V1 over V1. A1 is ST times L. For the AT, we have ST minus D times with L. Okay, let's take a look at the density term here. We know that the density is constant for incompressible flow. Therefore, rho 1 equal to rho T equal to rho. We can cancel out rho T and rho 1. That is number 1. Number 2, L for both of these area is the same. Therefore, we can cancel out length for both. Therefore, the equation becomes V maximum equal to, so V maximum equal to V1 times with ST divided by ST minus D ST minus D. So if we can rearrange this equation, it becomes ST divided by ST minus D times with V1. So this equation is the same as here. So we already derived the equation for V maximum for inline arrangement. Okay, so V1 is V. V is the flow of the fluid enters to the tube bank. Okay, so this is how we derive the V maximum equation for inline arrangement. So we know that there are two arrangements. One is inline, second is staggered arrangement. But for the staggered arrangement, we have two different equations. And these two different equations depends on the area of diagonal and AT. Okay. Let's take a look at this equation. So we will first we will see at the first equation where SD is greater than ST plus D divided by 2. The equation becomes like this. So V maximum equal to ST over ST minus dV. So here we will compare. So I will see the first condition here. So as we can see here, we will only compare AT and AD with A1. Okay, the first condition where AT is V maximum occurs at AT. Therefore, we want to calculate what is the V maximum. When we define that AT is V maximum, therefore this equation will become the same as equation in inline arrangement. Okay, so if AT is much more smaller than AD, okay, we compare AT and AD. If AT is much more smaller than AD much more smaller than AD. Therefore, V maximum occurs at AT. So we will derive the equation from A1 to AT. Okay, we know that AT is V maximum. So mass flow rate 1 equal to mass flow rate at T. So it is the same as inline arrangement equation, how we derive the V maximum. So rho 1 V1 A1 is equivalent to rho T VT times AT. So we know that VT is V maximum. We change it into V maximum. So rho 1 V1 A1 equal to rho T V maximum times with AT. So previously I already derived the equation for A1 and AT. So we know that A1 equation is ST times with L. For AT, we know that the equation is ST minus D times with L. Therefore, we substitute both of these equations into this equation. So rho 1, so V1, A1 is ST times with L equal to rho T V maximum times with ST minus D L. Okay, so we know that rho 1 is equivalent to rho 2, rho T equal to rho for incompressible flow. Therefore, we can cancel out rho T and rho 1. And another terms that we can cancel out is length. Length is the same for both. Therefore, length can be cancelled out. So rearrange the equation, we get V maximum is equivalent to ST divided by ST minus D times with V1. V1 is the velocity of fluid enters to the tube bank. Okay, this is the first equation for staggered if AT is much more smaller than AD. Therefore, V maximum occurs at AT. Okay, let's take a look at the second condition where AD is much more smaller than AT. Okay, this one. So what if AD much more smaller than AT? What will happen here? V maximum will occur at AD. So we will derive the equation from M1, A1 to AD. Okay, A1 to AD. So mass flow rate from 1 is equal to mass flow rate at D. Okay. So rho 1 V1 A1 equal to rho D VD AD. Now we know that VD is V maximum, therefore we change this equation VD, these terms into V maximum. So rho 1 V1 A1 equal to rho D V maximum times with AD. So as we can see here, when the flows enters, it will flows into 2AD. Therefore, area here, we have to include 2AD because this flow will divide into two sections. So for example, in the fluid mechanics, we have Q1, Q.1 equal to Q.2 plus Q.3. So it is the same concept as here. One flow divided into two flow. Therefore, to get what is the values or the summations of the Q here, we have to add 2AD. We have to add AD plus AD or 2AD. Therefore, here AD will become 2AD. So rho 1 V1 A1 equal to rho D V maximum times with 2AD. Okay, that is the equation. And then Row A1, we already determined what is the equation for A1. Right now, we want to determine what is the equation for AD. So, here, so we have tube, so the length of the tubes SD is from center to center. We want to find what is the AD, where we want to find the area from here to here. This is AD. We have SD from center to center. Again, center to center, we have here radius. Therefore, SD must be minus with radius here and here. Okay, so we have SD. So this is SD, but in SD it contains radius for both tubes. Therefore, in order for us to determine what is the AD, we have to, the length for AD here, we have to minus SD with radius from the first tube and radius from the second tube. Therefore, if we want to find the length and we want to find the area, so we have length of the tube times width. So SD must be minus with D over 2 for the tube and D over 2 for the first tube and D over 2 for the second tube. So SD minus D over 2 minus D over 2. So we have that equation, and AD is L times with SD minus 2D over 2. So we can cancel out 2. Therefore, AD is length times width SD minus D. So we have the equation for AD. We have to substitute AD into this equation to get what is V maximum. Before we substitute, we can cancel out rho 1 and rho D, because in compressible flow, we can cancel out density, because density is constant. And then this equation becomes V maximum equal to V1 over V1 A1 over AD, 2AD. Okay, so we substitute A1. A1 is ST L divided by 2 times with AD. AD is SD minus D. Okay, times with L and V1. So here we can cancel out length, and this equation becomes ST over 2, SD minus D times with V1. So this is equation for V maximum if AD much more lower than AT. So area for diagonal lower than area for AT. So V maximum will occur at AD. Okay. So that is staggered equation, and two conditions with two different equations for V maximum. So what is the importance of the V maximum? Because we want to substitute into the equation for Reynolds number D. Because we want to find what is the Reynolds number, therefore we have to find what is the V maximum. With the condition, first the arrangement of the tube, either it is in line or staggered, and then under staggered we have two different equations. If for the first one, AT much more lower than AD, therefore V maximum will occur at AT. And then we have the second condition where AD is much more lower than AT and V maximum will occur at AD. Then in order for you to determine what is the Nusselt number for tube banks, we will use the Zukaukas equation. As you can see here, 7.42. So this is equation proposed, correlation proposed by Zukaukas. So what you need to do here, in order for you to determine the Nusselt number, you have, for the first step, you have to determine whether that arrangement of the tubes is in line or in staggered. So that is the first step that you need to do to answer the question for tube banks. Either it is inline arrangement or staggered arrangement. And next, you have to determine the Reynolds number. For the inline Reynolds number, you will use equation Reynolds number. Then you have to substitute V maximum. Then we already derived the V maximum for the inline arrangement. So you substitute this value and then you get the V maximum, substitute into this equation to determine what is the Reynolds number. If you done that, you have to compare. Here we have range of Reynolds number from 0 to 100, 100 to 1000, 1000 to 2 times 10 to the power of 5, and then the last one 2 times 10 to the power of 5 to 2 times 10 to the power of 6. Each of these range have different correlation. So let's say your Reynolds number, you calculate the V maximum and then you get the Reynolds number. You get the Reynolds number range in between 100 to 1000. So you have to take this equation in your calculation. So you will plug in all the values in this equation. Okay? And then if staggered, then again you have two different conditions and you need to determine where the V maximum occurs. If you have V maximum at 80, then you will use this equation. If you have V maximum at AD, then you will use this equation, V maximum for V maximum. And then after that, you will substitute into Reynolds number equation to determine what is Reynolds number. From there, you will refer to this table where is your Reynolds number falls on. If your Reynolds number falls on 500 to 1000, then you will use this equation. Okay? And substitute all the values needed inside, and then you will get the Nusselt number. Then after that, if you want to find what is the H, then you need to equate with HD over K to determine what is the heat transfer coefficient. So the value of H. So normally we want to find what is the H value. Okay, this figure, this table is valid for number of tube banks with 16 or more rows. And if we get less than, if our tube rows less than 16, we have another steps to go through before we can calculate what is the Nusselt number. Now, what is rows? Let's take a look at this arrangement. This is inline arrangement. So let's say we have flow here, flows from, so our flows from here. So if your flows of the fluid are from here, so this is first column, second column, third column, and fourth column. And your rows, your number of rows, this is column, 1, 2, 3, 4. This is column. Rows is this. This is the first row, second row, third row, fourth row, and fifth row. So this is row and this is column. If your flows from here, okay, I change the colors to make you easier to differentiate. So let's say red color is your flows is from here. I change it, your flows is from here. Therefore, your column will be, this is the first column, second column, third column, fourth column, and fifth column. Then your rows will be, this is the first row, second row, third row, and fourth row. Okay? The key is you have to determine where is the flow. Then after you determine where is the flows of the fluid, you can determine the numbers of rows. Sometimes in the question, it will be given directly. Sometimes it will be given you the figure, and then you have to determine what is the value of rows. The importance of rows, because you want to find the Nusselt number, and you have to refer to the table 7.2. We have another tables for rows below than 16. So like I said before, if you have rows less than 16, you have to determine what is the Nusselt number, and you have to refer to table 7.3 where this number of row is below than 16. So how do we want to find the Nusselt number? So Nusselt number, we will find the Nusselt number for rows below than 16 by using this equation. Nusselt number is equal to F times with Nusselt number D. The steps are the same, but we have to add another terms here, which is F. F is correction factor. You have to find from here, you have to find what is the Nusselt number. You still have to use this, but after that you have to correct the values of Nusselt number by including or by multiplying with correction factors. How to determine the correction factors? So you have to see here in the table, you can see that 1, 2, 3, 4 up to 13. So what you have to do is, if you have inline arrangement and then your number of tubes is 7, for example, first you have to determine Reynolds number, and from V maximum you substitute into Reynolds number, and then you get the Reynolds number. You have to compare with this. You take a look at this figure 7.2 and where is your range of Reynolds number, and calculate the Reynolds number. For example, your Reynolds number in between 100 to 1000, and plug in all the values inside Nusselt number D. Then you have to find what is the correction factor. Let's say your numbers of row is 7, then you have to correct the values by multiplying with 0.96 from Nusselt number. 72. Okay, you calculate this Nusselt number, and then you have to correct that value by multiplying with 0.967. This 7 is for your number of rows, and then you have to multiply your Nusselt number from table 72 with 0.96. Okay, it is the same as staggered arrangement. Okay, so remember, you have, if your number of rows below that 16, you have another step. You have other step where you have to calculate by multiplying with correction factors. Okay, so this is the equation. Sometimes you have to find what is the rate of heat transfer. Normally we want to find what is the rate of heat transfer for the tube banks, and then from here we have to find what is H. How to find H, heat transfer coefficient? That is why you need to calculate Nusselt number. Okay, you have to determine what is the V maximum, and then you substitute into Reynolds number, and then from Reynolds number you have to see table 72 to find what is the Nusselt number equation, and then substitute all the equation to find what is the Nusselt number. If your number of rows below than 16, you have another tables to refer to, and then find the Nusselt number and equate with Nusselt number equal to HD over K to find what is heat transfer coefficient. Okay, and here we have delta T log mean. So delta T log mean, so to determine what is the rate of heat transfer for the tube banks, you have to use delta log mean. So what is the equation of delta log mean? Here we have delta log mean Ts minus Te minus Ts minus Ti over ln Ts minus Te, Ts minus Ti. So this is equation for log mean temperature difference. So as we can see here, normally in the question, sometimes in the question it will not give you this value Te, the exit for a flow. For example, if you have this arrangement, for example, so let's say we have number of row is 3. So we have T inlet, T in, that flows into this tube bank. And then we are not being given the values for T exit here. So how to find what is the T exit? Therefore, we have to use this equation, exit temperature, T exit equal to Ts minus Ts minus Ti exponential As times with H over m dot Cp. Okay. So As is N times with pi dl. Pi dl is area for surface area for a tube, and then times with number of tubes. Okay, for the mass flow rate, rho V and TSL, STL. So I will explain more on the mass flow rate in the example, because if I told you here, if I tell you here, it will be difficult to explain the mass flow rate. Therefore, I will bring the explanation for mass flow rate into our example video. Okay, same as AS. Okay, here we have different equation for Q dot. So m dot mass flow rate times with specific heat capacity times with exit temperature minus Ti. So you can equate the convection equation with this equation if you want to find what is Te. Te here comes from this equation. Okay, you have to rearrange. Oh, sorry, no. So the equation comes from the arithmetic means. So you can use this equation. For the rate of heat transfer, you can equate with m dot Cp